The first talk in the afternoon session is by Stephan, who will be continuing his lectures from day before yesterday, and he'll speak on wild fencing and divisor function.
Okay, so we want to make progress on the divisor problem. Let me just repeat 3 results which we need, which were obtained in the last lecture. So the first one is an explicit description of the error term in the divisor problem. Huh? Dividing, okay. So, good. Number 1. So from here it is revisible? Okay. Good, then number 1. So we saw last time that if n less or equal x, when we take the average of the divisor function, we get 2 main terms, x log x plus 2 gamma minus 1 x plus an error term which contains the phi function. So s less or equal square root x by x divided by s, where psi x is x minus box function minus 1/2 sawtooth function. So that is trivially estimated by square root x, and we want to do better. We want to improve the exponent. Our device is exponential sums, so we need to make the link to exponential sums. That's done we did it via Waller's theorem. And as a corollary, we get that, yeah. So let I in R plus be an interval. Let's assume I is size greater or equal 1. Length of I greater or equal 1. And G from I to R, the function. And we don't even need to make any conditions on that function. Then we can write a sum of this type. Then sum, yeah, let's call it S, element I, psi of GS. We can bound that by interval length divided by m plus 1 less or equal m, less or equal capital M, 1 divided by m, modulus, and then we take the sum over S, E of m, G, sorry, yeah, m, G, S. Where m is any parameter, any natural number you want to take. I write it here, where m is any natural number of our choice, will be optimized in the application. And the third result is the van der Korput bound. First, exponential sum estimate. Van der Korput. So we take a function that can I R plus be interval f from I to R. twice continuously differentiable. Such that, so the second derivative is in a certain range, such that lambda less or equal modulus, so that lambda should be greater than 0, modulus, second derivative less or equal alpha lambda for any x and I. So then we can obtain a bound for the exponential sum with that amplitude function. N element I, E of f, Fn is bounded by alpha length of the interval, lambda to the 1/2, plus lambda to the minus 1/2. Okay, and I said already in which case that is good. When this is non-trivial, that's non-trivial if lambda lies between, let's say interval length is n, between n to the minus 2 and 1. So it should be smaller than 1 in particular. Okay, so now let's directly apply that to the divisor problem. What do we get? Okay, so we prove the following. Yeah, call it the theorem. N less or equal x dn is the expected mean term. Then we prove 1/3 plus epsilon, more precisely 1/3 log x. And basically what we need to do is just putting everything together. Yeah, so from that lemma, we know what the error term is. We need to estimate that sum here. Then we can rewrite this using that lemma. So we have to show yeah. Okay. N less or equal square root x psi x divided by n is bounded by x to the 1/3 of x. Good, so first, as usual, it's reasonable to divide the sum into dyadic subsums. We can divide that into O of log x dyadic subsums. Dividing this to O of log x dyadic subsums. So we need to show some yeah, so when we do the Fourier expansion directly, then we get some tail, which is actually bounded in terms of the distance of that inside the exponential to the nearest integer, which is quite unpleasant. So therefore, it's good to use more refined devices, like what we used was Wahler's theorem, which allowed actually Wahler's theorem. So this allowed to approximate the psi function by another trigonometrical polynomial. And the modulus of the difference of these two functions is again bounded by a trigonometrical polynomial of length m. Yeah, so that tool allows that. Yeah. Yeah. Good, so we need to show that less or equal to y psi x divided by n is less x to the 1/3. So then, first of all, we can without loss of generality, assume that y is greater than x to the 1/3. Without loss of generality, y greater x to the 1/3. Good, so then let's rewrite that sum here. So is that actually visible, everything? Good. Would I start again here? We use that lemma. Good, so right. Sum y less than n, less or equal to y. Psi of x divided by n. Yes, this here. Interval length is y. So this is bounded by y divided by m, where we need to choose m suitably. Plus 1 less or equal m, capital M, 1 divided by m. Yeah. Okay. Y e of m x divided by n. Good. Huh? Anything wrong? No, I'm summing over n here. Yeah, so I divide into such dyadic intervals. We just need log x dyadic intervals of that form. And then for every y, we need to obtain that estimate here. So that remains x here. Yeah, so I should write y lies between x to the 1/3, less or equal y, less or equal x to the 1/2. No, actually we obtain x to the 1/3. And that will be sufficient. We will, for every y, we will actually obtain x to the 1/3. Yes, fine. So then we take log x of these sums, and altogether this gives x to the 1/3 log x, right? And so we get that estimate for the complete sum. Okay? Good. So then I can remove that part and can directly apply that lemma here. So what is the size of the derivative, the second derivative of that function? So f n is mx, or let's say ft is mx divided by t. So f prime prime p is of size approximately mx divided by y to the 3 if y less or equal t less or equal to y. We don't care about the constants. Yeah, so now we can apply that lemma, and what we obtain is y less than n, so y e of mx divided by n is bounded by the length of the interval is y times that to the 1/2 mx 1/2 plus, and then y to the 3 divided by mx to the 1/2. Okay, fine. And then we need to sum up over m. What we get is what we get is, m to the 1/2. M to the 1/2. X to the 1/2. Y to the minus 1/2. Plus. And that term, so we have 1/2. So we just get y to the 3/2 divided by x to the 1/2. So we cannot do anything about that term here. So when you plug in the largest y, that is x to the 1/2, you get precisely x to the 1/4, which is the limit of all what we can hope for. Okay, so this term is bounded by x to the 1/4. And now we need to balance these two terms here. So y divided by m equal to m/2 x to the 1/2 y to the minus 1/2. So that gives m to the 3/2 is equal to y to the 3/2, x to the minus 1/2. So we take m to be y x to the minus 1/3. Good, and we want an integer, so we take m equal to the box function y x to the minus 1/3. So this works because y is greater or equal x to the 1/3. So therefore I made that assumption here. And now let's plug in y. Let's plug in m. What do we get? So now the y cancels out. We see that the y cancels out. So this is bounded by x to the 1/3. And we are done. Okay? Everything clear? So that is a big progress from 1/2 to 1/3, but we would like to improve the 1/3 also. For that, we need a theory of exponential sums. You do van der Kopput and Weil. There are two processes in this theory. One is the Weil differencing, which we have seen already. This allows to drop the size of amplitude functions. And the second one is the B process, which uses Poisson summation and the saddle point method, which allows to shrink the size of the summation interval. So we will get new exponential sums from given exponential sums by these two processes, A and B process. So let's start with the Weil differencing. I remind you to what you have seen already in lectures yesterday. Good. Would I briefly write this? What? This allows transform x sums an element I, E of Fn, into new x sums with an amplitude function whose derivatives are of smaller size than that of Fn. So in particular, when we have a function which is outside the range of the van der Korput bound, whose second derivative is of size larger than 1, we can do Weil differencing or several Weil differencing and end up with a sum to which we can apply the van der Korput bound. All right, so let me remind you to the application of Weil differencing to Weil sums, so sums with of the form so one-dimensional sums of that form. Square or a larger power. So you've seen that in Professor Balasubramanian's talk. So the idea was you just square the modulus and you reduce this quadratic polynomial, which you have here, to linear polynomials. And then you can use the usual bound for linear polynomials. If you have a larger power, then you need to do that several times. Okay. Just as a warm-up, recall. So this is, you just multiply out a double sum of that form, alpha n1 square minus n2 square. So then the idea was to write n1 as n2 plus h. So h must be of size smaller than the interval length. So you can take h so equal I sum n2 element I. You write that as n2 plus h. So then n2 plus h also needs to lie in that interval. So this gives you a subinterval of I. So these two things are satisfied if n2 lies in a subinterval. You can write n2 element IH. IH is suitable subinterval. All right, so then we get E of alpha n2 plus h squared minus n2 square. And now the nice thing is that reduces to a linear polynomial in n2. So we get E of alpha 2n2 h alpha plus h squared. So we cannot do anything about the h square here. We put that outside. Just use triangle inequality. H less or equal I. Modulus 2 element I. E of 2h alpha n2. And then you know that is bounded by minimum interval length. Good, let's assume interval length greater or equal 1 again. So this is that, but so the interval length we just bounded by that interval length. 1 divided by 2h alpha. Yeah, and we've seen in Professor Balasubramanian's talk how to estimate these sums. So what we get is if alpha is A divided by Q plus O of Q to the minus 2, AQ integers, AQ O prime, okay, Q greater 0. Then this is bounded by, when you have a interval of length Q, you get the bound interval length. Moment, so you get, yeah, you get that here. Q times. Okay, but this interval may be longer. So one moment. So that would be Q log Q. Ah, yeah, okay, so yes, right. This, yes. Good. Q log Q, then the interval length I. Q. And that would be I divided by Q plus 1. So when you break that interval into subintervals of length Q. Yeah. So you get a bound of that type. Now good, and then you need to take the square root. And what you obtain is the original sum, an element I, E of Fn, is bounded by I divided by Q to the 1/2 plus. So then you get I to the 1/2. You get Q to the 1/2 log to the 1/2 Q plus. And here you get also, yeah, you get the same. So like that. So you save Q to the 1/2, a factor of Q to the 1/2 over the trivial bound here. And if Q is not too large, then this will be small compared to the interval length. Good, so that was the idea. Now let's see what happens if we have general exponential sums of this form and apply that idea. So in that case, we replace the function here by E of n. So then that turns into E of Fn1 minus two. And you use the same change of variables. And what you get is f of n plus h and 2. So now in general, you cannot reduce it like for a quadratic polynomial to a linear polynomial. So the question is, why should that be useful? So it's useful if h is not too large, because the difference is actually smaller than the original function. So let's consider the second derivative. That was what we needed to have under control for the van der Corput bound. So the second derivative, n2 plus h. This is by mean value theorem, h times f prime prime prime, third derivative. At some point m, let's say, m in n2 to H. So now, typically, the size of the third derivative. So if you have a m in the range of, yeah, let's say n, 2 in the range of capital N. So then the third derivative will be by a factor of n smaller than the second derivative. So typically we have, this is h times, yeah, the size of the second derivative divided by n, where we use assumption as in the Van-Koophout lemma. Yeah, so if h is small compared to n, then the size of the second derivative of the difference will be smaller. So actually we achieve something in the case when h is small. So somehow we need to make the idea work in such a way that we only keep h's which are small compared to the size of the other variable. So that is what we want to derive now. So the goal is define this idea in such a way that we keep only small h's. Okay, clear? What we need to do is clear? Yeah, okay, good. So when we have h of size about n, then we don't have an advantage as compared to previously. But for small h's, that function may be better than the original function f prime prime. Good, let's see how this works. Yeah, so we set psi n to be equal the characteristic function of the interval times e of fn. So that's supported only on I. Now, right. So we do a ridiculously looking thing. We copy the original sum h times. So that can be written as h times n element z psi of n. And now we throw in a shift here. So that is the same as h times, not h times, but sum, h equals 1 up to capital H, n element z, psi, n plus h. Just because the integers are translation invariant by shifts by integers. Okay, and now what we do is we use Cauchy-Schwarz inequality after changing the summation here. So this is equal to n element z, h equals 1 up to h, psi, n plus h. But we can restrict the sum, so we just need to assume n is such that n plus h is in the interval I for some h. So we can write actually n plus h element I for some h from 1 to capital H. Yeah. And to that we apply the Cauchy-Schwarz inequality. What we get is, this is bounded by, yeah, let's take the square on both sides. So I square the whole thing. Squared. Yeah, how many elements are in the set of n's? Satisfying a property like that. It's h plus the interval length, provided the interval length is an integer. So you get, so this is h plus interval length times sum n plus h element I or sum h 1 to h and then the square of that thing. That's h squared. Good. So then let's expand the square and rearrange summations again. So you get h plus interval length times m plus h. So the sum goes over n here. And here's that property. Good. Yeah, so you get k, l from 1 to h, psi n plus bar. So, and now we do again change of variables. So we say that this is m, and the difference of these two is k minus l is equal to, not both. So the difference of these two is h. Okay, so let's call this m here then. Good, then what you get is, this is equal to h plus I times so m element. Good, so let's just write m element z. H is less or equal, so the modulus of H is less or equal H. And you have yeah. M plus H bar M. And now you count KLs in this interval such that K minus L is equal to H. KL from 1 to H. K minus L is equal to H. 1. All right. And this number is precisely capital H minus modulus of small h. So then let's see what we got. Combining everything. So the sum square n element I psi of n is less or equal h plus I times and then we have that sum here. Yeah, so we can pull out the h. H. And then m element z. It's h bar. So m. Good, so now we divide by h. And so we get an element I. So one h goes here, one h goes here. 1 plus I divided by h. One minus that. All right. So now we just need to plug in the original function and see what we get. So recall psi of n is the characteristic function of n times e of fn. So now assume interval length is greater or equal h. Then what we get from this is the following. So square of n element I, e of fn. So this is bounded by twice that times I divided by h times, okay, so that can be estimated by 1. Simply, we use triangle inequality. H, that's not equal to capital H, E of F. Okay, sorry. N element IH, so now the subinterval again comes. So this is nothing else than n element I and n plus h element I. E of Fn minus Fn plus h. All right, so the order does not matter here, since we can replace h by minus h. So we can as well write Fn plus h. here modulus. So then you can still pull out the contribution of h equals 0 and use the symmetry. So it doesn't matter if we consider h or minus h. So therefore, this is bounded by 2i. So the contribution of h equals 0 is, in that case, this becomes 0. So this becomes just I square divided by h plus 2 times h between 1 and capital H and element IH, E of Fn plus H minus Fn modulus. Okay, so that is the bound which we need. It's similar to the Weil differencing process previously, but it's not just squaring out. We also do this trick, writing H copies of the exponential sum, shifted by 1 up to capital H. And then Cauchy-Schwarz. That gives this. And now the parameter h is restricted by a capital H of our choice. So we can optimize this h. So this will be trivial if h is equal to 1. So we need h a little bit larger than 1, so that this term is non-trivial. We cannot allow it to be too large, otherwise this term becomes large. So we need to balance these two terms. That's the idea. So that's the result, which I write as a theorem. In general, the A process takes this form, or the Weil differencing takes this form. Theorem. I need an interval f, a function from I to R, and h element n, such that so if h is larger than I, then we cannot get any savings. H less or equal interval length. Then the square of our exponential sum, and I, E of Fn squared is bounded by 2 I squared divided by h plus sum 1, okay, 2 times h less or equal capital H and element IH, E of F n plus h minus f of n. Let's write down this IH also explicitly. Here, if I is the interval from A to B, then IH, since we have these two conditions, n element of I and n plus h element of I, we get maximum A plus h, minimum B minus h. So a subinterval, but if h is small compared to the interval length, then it will not deviate much from the original interval, I. Good, so that was a long calculation. I've managed to reduce the size of the amplitude function, but the cost is that we get a sum over exponential sums. So now let's apply that to a situation when the derivative, the second derivative is larger than 1. What we do now is combining Weil differencing and Vanderkorput bound. So for the divisor function, we don't get anything new yet. We need also the B process. But for the zeta function, subconvexity for the zeta function, we get a while bound, in fact, by the following combination of the A process and the van der Kopput bound. Okay, so that's pretty straightforward. So now assume f goes from I to R, such that the third derivative is bounded instead of the second derivative by lambda and alpha lambda. So then what we need to bound now is this difference. We just use the second derivative of this difference. We just use the mean value theorem from calculus. By mean value theorem, f prime prime x plus h minus f prime prime x is equal to h times third derivative at some point x0 or some 0 in x2 x plus h. So we got the following bound, f prime prime x plus h minus f prime prime x, bounded from below by h times lambda, modulus of h times lambda, and from above by alpha modulus h lambda. Good, so now we have a result for the second derivative under this hypothesis, and we can directly apply the van der Kopput lemma to that sum. And we sum up everything and we choose h optimally. So let's do that and see what we get. And then we apply it. So by van der Kopput. Now, let's call this a square. Oh, okay. Am I audible? Good. Okay. So S square, modulus S square is bounded by, so what did we get? Interval length. Square divided by h plus some 1 less or equal lesser h less or equal h. And we plug in the van der Kopput bound, getting alpha length of I times that bound. Okay, so we need that bound, alpha h. Yes, alpha I. And so our lambda is replaced by that. Lambda 1/2. Yeah. Plus lambda to the minus 1/2. Right, so then what happens if we sum up? So then we get that. Let's forget the alpha. So we assume it's bounded by some constant. In application, that will be the case. Let's just keep the dependence on the lambda here. Okay. So then we get h to the 3/2 I lambda to the 1/2 plus, and this term here gives h to the 1/2. Yeah, h to the 1/2 lambda to the minus 1/2. Good, so now we need to balance terms. One moment. Did I forget anything? So I forgot one factor here. To divide by h, because we divided by h here. So we had a h in the numerator and we divided by h square here. So that factor I forgot. Okay. So then this turns into 1/2 and that turns into minus 1/2. So now everything correct? Yeah. So now we need to balance the terms. We should balance that term and that term. So we choose h in such a way that these terms are approximately equal. So that gives h to the 3/2 is equal to I lambda to the minus 1/2. So we get h is I to the 2/3 lambda minus 1/3. And then we plug in and get, so this is bounded by. Yeah, we should take again a box function of that, but let's not go into these subtleties. So what we get is yeah, lambda to the minus 1/2 I square one moment. One half. Okay. I forgot one more factor. I'm really sorry about that, but I completely forgot the whole factor. So that's actually I over h. Good. So then what do we get? So then we get a square here, and we get an extra factor of I here. Good. So then we have that equation, and there is no I here. Okay. So this will be equal to lambda to the minus 1/3. Good, and then we plug this in, and what we get is following bound. S squared is bounded by I squared times. And we have a lambda to the 1/3. So then we balanced with that term. So now we need to plug in into that term, and what we get is lambda to the 1/6. So lambda to the minus 1/3. Right? Yes. Okay. And then taking square root gives S is bounded by I, lambda to the 1/3 plus I to the 1/2, lambda to the minus 1/3. Okay, so 1/6. Okay, we can state that as a lemma. So that's a combination of file differencing and van der Korput suppose f from I to R is thrice continuously differentiable. And f prime 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 x is in the range of lambda. Then our exponential sum is size I lambda to the 1/6 plus I 1/2 lambda to the minus 1/6. So that is good when the third derivative is less or equal 1. So that applies also in situations when the second derivative is greater than 1. So now, as I said, for the divisor problem, it does not give anything new, but for the zeta function. So let me sketch that, just how we get a while bound for the zeta function. Okay. Yes, so that factor needs to be there. Sketch. Yeah, so we may apply the approximate functional equation. We consider zeta 1/2 plus IT. Okay, let's say that is S here. Want to get a bound in terms of T. So then approximate functional equation in the sharp cutoff version takes that form. So n less or equal, square root T, actually T divided by 2 pi square root n to the minus S plus, here we can take the same length n to the 1 minus S. So then plus some extra factor, let's call it HS, plus some small error. Okay, so I take the length of these two Dirichlet polynomials the same. HS has modulus 1. So the size of that will be the size of that. Good, so we just need to consider that here to get a bound for the zeta function. Okay, we rewrite this as an exponential sum. Right. Square root p divided by n to the minus s equal to pi n to the minus 1/2 times minus t. So then we have this extra factor which can be removed using partial summation. So let's just care about what is some n in the range of that term. So then we know what this will give just by dividing square root of this interval length here. Huh? Huh? Yeah, just so we have an extra factor here. Good, so this can be rewritten as I said. Yeah, okay, I write this once again. N to the minus 1/2 times e of minus t log n divided by 2 pi. So we just remove that using calculation. All right. Yeah, so let's deal with n in the range of square root t. Simplify things. N to the minus it. So this is bounded by. We need to find the size of the third derivative. So in that case, fx is minus 2 pi log x divided by, sorry, t pi. So the size of the third derivative is exactly t divided by that squared. What? To the 3. Good, and x to the 3 is of the range in the range of square root t, so we get 1 divided by t to the 1/2. So now we can apply that lemma which we just obtained by combining Weil differencing and van der Corput bound. So what we get is interval length is the square root t times 1/6, yeah, 1/6. That thing to the 1/6. 6 plus. And then back to the minus 1/6 times interval length to the 1/2. So that would be fourth. Okay, 1/2 minus 1/12 is 5/12. And this is here 1/3. This is 1/3. Yes. Okay, so what you get is that dominates actually, that gives 5/12. And then from here we can see what we will get when we do everything the correct way. So we will get zeta 1/2 plus it is bounded by. So we need to divide that by square root of the interval length, accounting for this factor here. So that means t to the 5/12 divided by t to the 1/4. is equal to t to the 1/6. Hmm? Huh? Yeah, 1/12. Yeah. Good. So we should also, I mean, we will certainly divide into dyadic intervals again. We will get another log factor here. But roughly speaking, 1/6. So that's a while bound here. While bound? Yeah, that's quite nice that our theory already gives the while bound. So to get that further down, we need to work harder. We need to introduce another process, and that we will do in the next lecture. So what is the record of Bogan? 84, okay. Bogan. 1/6 minus 1/84. Okay. Some improvement. Yeah, so the big step was really to come down from 1/4 to 1/6. Okay, so we will apply then these A and B processes to that problem and the divisor problem again, and see what we can get from that. I will be very sketchy in the next lecture, and because I want to say something more about other methods. Okay, I think I stop here. That's enough.
Are there any questions?
Yeah, so if you have smooth weights, yeah, it will not get better, but yeah. Yeah, so good, the while differencing, that there will be, good, then there will be a product of two weight functions. Okay, that is fine. In the B process, it will get simpler because, so then Poisson summation is nicer. So when we have a smooth weight, Poisson summation works better than if we have some discontinuous function. So we don't need to care about certain error terms when we work out this B process. Yeah, it's always advantageous to have a smooth weight. And so the second term is the same, just, so this is minus 1/2 minus IT, and this is, yeah, so this is 1/2, moment, plus IT. Yeah, so that's the same, minus 1/2, sorry, minus 1/2 plus IT. So it's just conjugated then. So we have the same weight, n to the minus 1/2, and so what happens here? Okay, I have made a mistake here. S minus 1, because S is replaced by 1 minus S. Sorry about that. Good. Yeah, so we will get minus 1/2 plus IT. And the length of the sum is the same, and this factor here is also just of modulus 1. So that is fine.
Okay, so if there are no more questions, please thank Stephan again.